In this movie, we'll look at state machine diagrams, which we use to model the state of things in the system. We'll look at the origins of state machines and the two types that are defined by UML, and then we'll look at their purpose in modeling the behavior of elements of the system in terms of states, in understanding the important state-dependent behavior of objects, and in analyzing how state changes over time. We've referred to the state of objects in other places in this course, in object diagrams, in sequence diagrams, and in activity diagrams. However, it's in state machine diagrams that we actually model state and how it changes over time in response to the events in the system. State machines in UML are a type of finite state machine that models states and the transitions between them. They're based on the notation for state charts developed by David Harel and described in his book, Modeling Reactive Systems with State Charts. UML has some semantic differences from Harel's approach. UML defines two types of state machine: behavior state machines and protocol state machines. Behavior state machines are used to specify the behavior of some part of a system that is being designed in terms of states and the transitions between them. Technically, such a state machine is owned by a behaviored classifier, which is a classifier that has behavior associated with it, and specifies a behavioral feature of such a classifier. This could be a use case or an operation of a class. Protocol state machines are a subclass of behavior state machines and are used to specify the usage protocol or life cycle of a classifier, usually a class or an interface, whose instances must conform to the permitted states and transitions defined in the state machine. A protocol state machine also defines the way that users of the services of objects of a class can interact with those objects by sending messages. In general, we use state machines to understand the state-dependent behavior of parts of the system. Some systems have a lot of behavior that depends on state, and others don't. State machine diagrams are useful for those that do. External events trigger changes of state through transitions. The response can depend on the state that the part of the system being modelled is in. As a simple example, in a banking system, a customer may withdraw money from a current account or checking account. If the result of the action is to reduce their balance below zero, the account will go into an overdrawn state. If they then try to withdraw more money, the response to that event will be different because the account is now in the overdrawn state. Objects may change state over their lifetime. They could be long-lived like bank accounts or short-lived like shopping baskets in a web page. Behavior state machines model the behavior of parts of the system, usually use cases or operations. A common example is the use of an automated teller machine whose behavior goes through a number of states, starting with the event of a bank card being inserted into the machine, then the user keying in their PIN, and so on. In the example here, which is a state machine for the use case directly control device via browser, the state machine models the different states of the user interface and the legitimate paths that the user can take through the user interface as they interact with it. Protocol state machines model the legal sequence of state changes for a classifier such as a class or interface. This provides a specification that can be used when consuming the services that instances of a class offer. For example, a programmer writing code to use a database connection needs to know that it's necessary to create the connection and then open it before trying to execute queries against tables in the database. The example here shows a simple state machine for an open-closed device, which has to be in the connected state and can then be in one of four substates: open, closing, closed, and opening. We'll look at both kinds of state machine in this chapter, but we'll start with the basics of states and transitions that are common to both.